So the theory of special relativity really revolutionized our understanding of space and time, and yet that powerful change was based on only two simple axioms. And one of those axioms has been with us for several hundred years, and that's that physics is invariant between all inertial reference frames. An inertial reference frame is related to another inertial reference frame just at most by constant velocity. And so if you do experiments in one inertial reference frame, you get exactly the same results of that experiment in another inertial reference frame. And in fact, if you add one tiny little axiom to that, if you just require that in one inertial reference frame, if you think A causes B, then every other person in every other inertial reference frame has to also agree that A causes B, then you can go from that to show that either space and time work just like the Galilean transforms say they do, or they work like the Lorenz transforms. So in other words, either time is universal and absolute, or space and time are inextricably mixed up and they mix together as you change between inertial reference frames. So really what this second postulate of special relativity is telling us, and the second postulate is that light travels at the same speed in all inertial reference frames, it's telling us that we live in that second kind of universe, where space and time are in fact inextricably linked together, and that you can change from one to the other as you change between inertial reference frames. Now these two postulates of special relativity are all we need to know to figure out exactly how all inertial reference frames are related, and indeed the structure therefore of that space-time and its vector space. And the speed of light comes into that, but light itself is really just a historical accident. In fact, any massless particle has to have exactly the same properties as light does. But electromagnetism was the first physical thing that we discovered whose description behaved in a manifestly special relativistic way rather than something that obeyed the Galilean transforms. So let's look at the structure of the theory that these two postulates imply. In special relativity, we deal with objects in a four-dimensional Minkowski space. An example would be the position vector, where of course we're dealing with a position in space-time, not just space. And if we change inertial reference frames such that we just do a translation, we know how to do a translation on this. If we do a rotation, we do a rotation on the spatial degrees of freedom only. Or if we do a boost, which is where we do a change from one inertial reference frame to another one going at a different velocity, then we apply the following Lorenz transforms, where we can write that in graphical form, where we've applied the boost by a velocity v along the direction of x. We learned how to use the metric to get the coefficients of the covectors in terms of the coefficients of a vector, where I've introduced a lot of notation. So these objects with the index up the top are vector components. These coefficients with the index down the bottom are covector components. This thing here is the metric, which is just the diagonal matrix with the diagonal elements being 1, -1, -1, and -1. This is whatever vector you might like. For example, it might be a position vector, which would make this thing over here a covector with coefficients. Note we've used Einstein summation notation again. In four vectors, you always have one index down and one index up if you're going to sum over them. You never have 3, for example. And so you can see on the left-hand side, we have a free index of mu. So on the right-hand side, we've got this free index and this dummy index, which we're summing over. Now, the importance of knowing about the covectors is that you know what the inner product is. So the inner product between a vector B and a covector A can be written like that, which is just the same as, so writing in terms of the two vector components there, and it's just, so it's almost like the Euclidean inner product, except you've got a minus sign on all the space-like components. Okay, now the reason that inner products are important is that they are scalars. They are actually independent of which reference frame we're in. In fact, that's how we figured out that this is what our inner product was. So if we change reference frames, we still get the same number. They can define real physical quantities. One of the most obvious physical things that they define is the distance between 2 points. So supposing we have a space-time point R1, which is a 4 vector like this, and we have another one, R2, then the distance between those is going to be a difference vector, which is going to be defined by the difference in times and positions in each direction. And of course, the size of this, to take the size of this in any metric space, what you do is you take the inner product between this vector and itself, and that inner product gives us a number. And that number, you'll note, can be positive or negative. So technically this inner product is known as an indefinite inner product. So draw our axes. We'll do two spatial dimensions. We'll have an x and a y, as well as a t here. So if you happen to be going at exactly the speed of light, then you'll be somewhere on this surface, which is known as a light cone, and that must have delta s squared equals 0. Now it looks like a cone in this number of dimensions. It looks like a triangle if you go down a dimension. It looks like something crazy if you go up a dimension, but we always call it a light cone. And so anything that has an interval of 0, a distance between 2 points on it as 0, can always be connected by a light signal. If we take 2 points that are outside this light cone, however, if we take them like this, so maybe we take the origin and this point here, then these 2 points, if we look at the interval between them, then we've got to have more position than we have time. So in fact, the interval is going to be negative. And we call this separation space-like, because there's always some reference frame which is exactly like space. There's no time interval between those two events at all. They happen at exactly the same time. Correspondingly, if we go inside this light cone closer to the time axis and look at two events in there, then they are separated by an interval that is positive, and that's known as a time-like separation. And what that means, of course, is that an event here can cause another event there. There's some reference frame when in fact this event and that event happen in exactly the same place, just at different times, and so the earlier one can affect the other one. When we're talking about a space-like thing, in fact, these two events can't cause one another because there's no way of sending a signal. We haven't shown that yet, but in fact the speed of light is the maximum speed at which you can send information from one place to another. One quick explanation of why that's impossible is that if you have the ability for space-like events to affect one another, then a space-like event here, there's no particular reason to say that this one out here happens before or after the one at the origin, because in different inertial reference frames you get different answers to that. So if you can cause one to affect the other, that seems okay, but you could then say that that point there and that point in here, you can't tell which one becomes earlier. So if you could send courses forwards and backwards along these lines, you could actually have something in the future inside this light cone affect something in the past inside this light cone. And so you'd have backwards causality. And so you could set up all sorts of paradoxes from that. For time-like separated events, there's a very real interpretation of this interval, delta S. Remember that there's an inertial reference frame where any two time-like separated events are actually at exactly the same place, just happening at different times. And that means that for the interval, we can ignore all these terms, and we just have that delta S is equal to C delta T when we take the square root of both. And so that delta S is just the time interval between those two events in that particular frame. So in that reference frame where you're sitting at rest with an object, if you measure its time in that frame, that's called the proper time. So supposing I want to calculate the proper time for an object that's accelerating. In other words, its world line might be having all sorts of curves. It always has to be inside the light cone or an instantaneous light cone, but it can curve and swirl around as it accelerates. So supposing I want to calculate the proper time for that object, how do I do that? Well, it's quite simple. What I do is I break up this line into lots of little pieces, lots of short segments where it's basically moving at a constant velocity, and then I calculate the proper time for that in that frame, and then I add them all up. So the proper time, which we usually use tau for the proper time, is going to be equal to the integral of all the little pieces of proper time from all the little pieces of the integral, which is going to be the interval divided by the speed of light, technically. Many authors will set the speed of light to 1. Please stop them. And we know what the interval is in terms of the actual coordinate system you might be using. So as the velocity changes, we'll find small corrections to your time. So if your velocity is very low, you'll find that the proper time is more or less equal to the actual time that you measure in your coordinate system. But as your speeds get close to the speed of light, you'll find that the proper time and the time that you measure in your arbitrary coordinate system do change.